Now, let's define a vector quantity and a scalar quantity. Now, these are very important things that you must notice uh, because these two things are going to be talked about for the majority of your educational life because they'll, especially if you're going into physics or any kind of engineering program, these two things, vector quantities and scalar quantities, they'll be talked about almost all of the time. And that is why it is very important for you to have a firm grip on what they are. So, a vector quantity, or simply a vector, is a quantity that possesses both a magnitude and a direction. Remember this, a magnitude and a direction. And these are some examples, and I'll get to them later what they mean. Let's first discuss the basic definition of a scalar quantity. So a scalar quantity, or a scalar, is one that possesses only a magnitude. So you see that a vector has a magnitude and a direction, but a scalar quantity has only a magnitude. It does not have a direction. So examples are these. Now, let's see. The first example, there is a very good way to explain what this actually means. Displacement. Okay? Displacement is a vector quantity. And another example of a scalar quantity is distance. Now, what is the difference between distance and displacement? Simple, really. It's the direction. So, for example, if you have this path here, this is A and this is B. Now, you can go along this path to get to B. You can go along this path to get to B, or you can like go around many paths to get to B, right? But here's the thing, that is a distance, okay? But what is a displacement? Let's just use another color for it. A displacement is the shortest distance between 2 points. So a straight line between A and B, that is the displacement. The other paths can be distances, because in a distance the direction does not matter, but in a displacement the direction is a straight line, the shortest distance between 2 points. That is an example of a difference between a scalar quantity, which is the distance, and a vector quantity, which is the displacement, right? So yeah, that's a very basic definition of what a vector quantity and a scalar quantity is. So yeah. Let's see the representation of a vector and the modulus of a vector. Now, let's first discuss how to represent a vector. So, a vector is represented by a line segment along with an arrowhead. Okay? And it is denoted by a directed line segment, a bold-faced small letter, or an underlined small letter. Okay, so here are how. So for example, if you have a vector going from A to B, right? Here's a vector AB. Simple, really. It can be denoted like this. So you write down the terminal points AB with an arrowhead that goes from A to B, right? See this arrowhead over here? It is going from A to B. That is how it is represented, since the vector itself is going from A to B, because the terminal point or the head of the vector is at B. So here's one way to represent it. Another way is to just write down a small letter to represent it, and or an underlined small letter, right? It's better not to use this one, really. It's better to use the other two, because this becomes a bit ambiguous, and these two the two two points with the arrowhead, like the A is the initial point or the tail of the vector, and B is the terminal point or the head of the vector. Write those two down, and an arrowhead above them. This is probably, in my opinion, the perfect way to represent a vector. And the last one, this one, also is a fine way because the underline underneath the letter also explains that it is a vector. The second one can be a bit ambiguous, but you can use that as well, really. So, the modulus of a vector. The modulus of a vector is the absolute value or the magnitude of the vector. So since magnitude always has a positive sign, okay, so the modulus of vector AB is denoted like this: AB with between two bars, right? And what this really means is that obviously a vector has a magnitude and a direction, right? So it can be both negative and it can be positive, but the modulus is the absolute value of the vector, right? So for example, if you had a velocity, right, and let's just call it let's just say that velocity AB, right? Oops, sorry. Velocity AB. Oops. And we need to find the absolute value. So we need to find, and let's say that AB, the velocity, is equal to, let's say, -3, right? The absolute value of this would be AB in the brackets, and that would be equal to +3. Okay, and you'll later on see how this is actually valid, why we need to do this really. But remember that the modulus of a vector is the magnitude without the direction. The negative sign over here represents that it is going in the opposite direction, right? So the magnitude of it will just be 3. It will not be -3 because we're ignoring the direction when it comes to the modulus. Okay. Now, let's see the multiplication of a vector by a scalar. So we multiply a vector with a scalar. And let's also discuss equal vectors and parallel vectors. Okay, so let's first discuss the multiplication of a vector with a scalar. So the multiplication of a vector v, okay, by a scalar k. Okay, so v has a magnitude and a direction, but k is a scalar. So you're just multiplying k with v. So the multiplication of a vector v by a scalar k is a vector. So the multiplication of a vector and a scalar results in a vector. So let's just see, a vector into a scalar is equal to a scalar. So that's one thing to note, okay? And it is a vector whose magnitude is k times that of v, and it is denoted by kv. Simple. So basically you're just increasing the magnitude of the vector v by k. Simple. So if k is positive, then v and kv are in the same direction. Obviously, because let's just say you have a vector v which is equal to, let's say, -2, right? So if you have a scalar k which is basically equal to, since it is positive, we're discussing the positive first, so k is equal to, let's say, 4. So k v is equal to -2 into 4, which is equal to -8. As you can see, both v and kv are negative, so they're in the same direction, right? But if k is negative, then kv and v are in the opposite direction. So let's just take this, let's just take two other vectors. So let's just say in this case, v is equal to, again, -2, okay? And let's just say k is equal to -4 instead of +4. So when you have k v, that will be equal to -4 into -2, which is equal to +8. As you can see, v is negative, but kv is positive, right? So V is in the negative direction and KV is in the positive direction. So they're in opposite directions. I hope that clears things up. So let's discuss equal vectors. So two vectors A, B are said to be equal if they have the same magnitude and the same direction. So this is equal to this. So the modulus of AB is equal to the modulus of CD, which means that they have the same magnitude and A to B is in this direction and C to D is also in the same direction. So basically there is no difference between this vector and this vector because they have the same length, which means they have the same magnitude and they have the same direction. A is the initial side, it is down, it is below B, and C is also the initial side in the other case and it is also below D. So A to B, B is the terminal side and in the other case D is the terminal side. So both vectors are equal in magnitude and they're also in the same direction. That's a very simple concept really. If both vectors are the same, they look the same, they are the same. So let's discuss parallel vectors. Now, two vectors are parallel if and only if they are non-zero scalar multiples of each other. So they can be in opposite directions because let's just say this is vector AB, right? AB. And this is negative AB because it is in the opposite direction to the original vector AB. But it is a scalar multiple because negative AB is just -1 into AB. -1 is the non-zero scalar multiple, right? So AB and negative AB are scalar multiples of each other. So they're parallel vectors. And another example is this, 3 by 2 AB. The magnitude of this vector is greater than that of AB, but it is a scalar multiple. So basically 3 by 2 AB is simply just 3 by 2, which is a scalar, into AB, which is the vector. And so since it is a scalar multiple of AB, it is parallel to AB, since it has the same direction, right? It's just the simple rule to remember is that two vectors are parallel if and only if they are non-zero scalar multiples of each other. Simple. Now let's discuss the addition and subtraction of two vectors. So there are two ways to add two vectors. One is the triangle law of addition and the other is the parallelogram law of addition. Both serve the same purpose and will give you the same result, but they're just two different methods and you basically just decide which one you're comfortable with. That's the beauty of maths. So the triangle law of addition. If two vectors u and v are represented by two sides a, b and bc, so this basically means that the vector ab is equal to u and bc is equal to v, right? And they're the two sides of a triangle such that the terminal point of u coincides with the initial point of v. This is a very important thing to remember. The terminal side of u or the arrowhead of u coincides with the initial point of v or the tail of v. So the head of u coincides with the tail of v. Then the third side, AC, that goes from A to C, gives you the vector sum u plus v. So AB plus BC is equal to AC. Simple really. And that just means u plus v is equal to AC. Here's an example. So this side AB or u and the terminal side of AB, which is this point here, whoops, it is the initial side of BC, right? The terminal point of AB is the initial side of BC. Simple. And BC is V. So if you draw a vector from A, the initial side of A, to the terminal point of C, that will give you AC, which is U plus V. But remember, this only works when the terminal side of B coincides with the when the terminal point of AB coincides with the initial point of BC, right? And basically the final stretch that connects the initial side of A with connects the initial side of AB with the terminal side of BC is the sum of the two vectors AB and BC. Simple. And another way to do this is, and let me just explain why we do this. For example, if you didn't have this particular vector in this format, if you had it, let's say, in this format, that you had AB like this, and if you had BC like say this here, right? Then you could just take it from this side and put it on that side and connect them and use the triangle law of addition. But it's simpler if it's just given to you. The other way you can do this is with the parallelogram law of addition. And it says that if two vectors u and v are represented by two adjacent sides, AB and AC, of a parallelogram as shown in the figure, then the diagonal AD gives the sum or the resultant of AB and AC, right? So here's the thing. The two adjacent sides are AB and AC. So this is AB, this side here, and this is AC, both emerging from the same point A. And you need to find their sum. Since they have a common point A, they both have the same initial side. All you have to do now is make a parallelogram, right? So basically draw the vector AC, a parallel vector of AC actually, or an equal vector called BD, which is this here, right? And then just from D, connect the point D with point C. Oops, sorry. And now you have a parallelogram. So then you just connect the point A and the point D, and that vector AD with the initial side, with the initial point again at A and the terminal point at D, that will give you the sum of the vectors AB and AC, or U plus V. And that is the parallelogram law of addition. So you can use both of them with whichever one is more suitable for a particular question, whichever is easier. You can use both of them, honestly. Like, again, if you had this question in which they asked you for the sum, you can just, like I told you earlier, this side AB, this one here, you can just shift it to the tail of C and draw CD like this, and that'll give you the method using the triangle law of addition. But you can also use this parallelogram law of addition, right? So yeah, that's the addition and subtraction of two vectors. Now let's discuss the definition of a position vector. So it's really simple. Oops. The vector whose initial point is at the origin O and whose terminal point is P is called a position vector of point P, and it is written as OP. Simple. There's nothing more to it. So if you have an XY plane, then the necessary things that you must remember for a vector to be a position vector is that the initial side must start at the origin. And wherever it goes, for example, if this is point P, which is the terminal side, right? Then this vector OP is this, right? Simple. So the position vectors of point A and B relative to position O are defined by OA and OB, right? And here, in the figure by triangular law of addition, simple. This is, let's say that this is the origin O. If you had an XY plane, this would be the origin. So let's just say this is an XY plane, okay? And this starts at the position O, the origin. So the vector OA is this one, right? And the vector OB is this one. So if you use the triangular law of addition, you can see that the terminal side of OA, which is A over here, coincides with the initial side of AB, which is again A, right? A is the terminal side of OA, and the initial side of AB. And if you connect them, that gives you the vector OB, right? So OA plus AB is equal to OB. Simple. And by just rearranging the terms, you can see that if you write down OA as A and OB as B, and AB is what you have to find, then simply take A to the right hand side, it becomes negative. So AB is equal to B minus A. So AB, this vector AB, is equal to B minus A. So you subtract this vector from this vector and you get the resultant. Now let's discuss what the magnitude of a vector is and its properties. So to find for any vector u with xy as its coordinates, right, in a two-dimensional plane, r square, this just means it's a two-dimensional plane, we define the magnitude, norm, or the length of this vector u basically like this. Okay, now the terminal sides basically from the origin O. In this particular example over here, it says that the initial side of vector u is at the origin, and this is its terminal side P, right? And its coordinates are x and y, right? Now, to find the magnitude, first you must know the notation. So basically, the magnitude of u is denoted like this, or it can be denoted like this, or it can be basically just, yeah, these two ways are the denotions. Now, the vector u, in this case, can also be written down as OP, because it goes from O till P. The O is the initial side, and P is the terminal side. So obviously, the magnitude of u, if it can be written like this, it can also be written like this, right? Now, to find the value, you just used this formula. Basically, just square the x value and square the y value, add them up and take the under root. Really simple. Now, here's the thing. In this particular example, the initial side already exists at the origin. So that makes life a bit simple for us, right? But in cases where, for example, you do not have this vector over here, right? If it does not start on the origin, if it starts somewhere else, you'll have to find its relation, its coordinates from the origin, so that you can find its magnitude. Okay. Now, here's the thing. What really is the magnitude? Well, magnitude is basically the length of the vector without any directions, right? So it is a scalar quantity. So basically, obviously, over here, from this info, you cannot tell what the magnitude, the length of this vector is. It just tells you that it has an x value and a y value. So to find its length, you need to apply this formula. Simple. What are the properties? Well, if the magnitude, let v be a vector in the plane, and let c be a real number, so a scalar, right? It says here that the magnitude is greater than or equal to 0, and magnitude is equal to 0 if and only if the vector v is equal to 0, right? Now, basically, the magnitude is 0 if the vector is a null vector, right? That's just self-explanatory, because if it is a null vector, a null vector has 0 length. It is nowhere. It's just 0. It's nothing. So obviously, the magnitude will also be 0. And here's the second property. If you take a scalar, c,
and multiply it with the vector v and take its magnitude after that, it's basically just equal to the magnitude of c multiplied with the magnitude of the vector v. You can apply both of these are interchangeable, right? So yeah, that's about it. Now let's discuss the definition of a zero vector, a unit vector, and a negative vector. First, let's discuss the negative vector, because to understand what a zero vector is, you must first understand what a negative of a vector is. So the negative of a vector is basically any vector. So let's say this vector u, when it is multiplied with a scalar -1, we'll call that alpha, right? So alpha u will basically give you the negative of the vector u. So we'll multiply the scalar -1 with the vector u. If the vector u is equal to xy, then when you multiply the scalar -1 with x and y, you'll get negative x and negative y. It's really just that simple, right? So basically, the directions are inversed. And this new vector is denoted by negative u. So basically, the negative of vector u is negative u. Really self-explanatory, honestly. I don't need to explain this. And it is also called the additive inverse of u, or the negative vector of u, right? Now, what is a unit vector? A vector whose magnitude is unity is called a unit vector. Simple, really. So let's say you have a vector A, right? Its unit vector will be denoted by this, A with a hat on the top, right? You'll call this a hat, really. So the unit vector in the direction of A is given by this, right? The unit vector of A is basically equal to the vector A divided by its magnitude. And let me just draw out to explain what this really means, because this is important. So if you have, say, this vector over here, right? Let's say it has a magnitude of 3. It's when you divide this vector by its own magnitude, you'll get a vector in the same direction, in the same shape, but with a magnitude of 1. So this vector here is the unit vector of this vector here, right? Simple. Now, let's see what a zero vector is. And it's very self-explanatory. A zero vector is basically this vector over here. It's called a zero or a null vector. It has nothing in it. 0, 0. And if you have a 3-dimensional vector, it will be 0, 0, 0, right? So how do we get this? Simple. If you add a vector u with its negative vector minus u, that'll give you 0, right? So if u is equal to x, y, obviously negative u will be equal to minus x minus y. And when you add them up, x will be added to negative x, y will be added to negative y. So x minus x is obviously equal to 0, and y minus y is also equal to 0. And that just gives you the null vector 0, right? Simple. Now let's discuss the ratio formula. So it says here that let A and B be 2 points whose position vectors are A and B, right? So these are the points A and B. This is A and this is B. And the position vectors of these points obviously are A and B. And basically what the position vectors are basically the vectors running from the origin O. So the position vector A is basically equal to the vector that runs from O till A. So basically A is equal to OA, right? Similarly, B is equal to OB. So I've discussed what position vectors are earlier. So if you do not know what they are, please refer to that video. Now, it says that if a point P divides AB in the ratio P ratio Q, right? So this is the point P over here, and it divides this AB, this vector AB, by the ratio P and Q, right? Then the position vector of P, what is the position vector of P? The vector that runs from O till P, and that is R over here, right? So how do we find R? By this formula. Now, actually this is not equal to P, this is equal to Q. So basically QA plus PB is over P plus Q is equal to R. How do we come to this conclusion? Well, simple. As you know, it says that this point P divides AB into two parts, P and Q. So AP, the vector AP plus the vector PB, the vector AP divided by the vector PB is obviously equal to P over Q, right? So AP ratio PB, is equal to P over Q, right? So let's see how we came to this formula. Let's just cross multiply these, right? So basically that just means that QAP is equal to PPP, right? Now, here's the thing. We must replace this AP and PB with the known values that are given to us, right? So let's just see what this means. Look at this triangle over here, this one, right? From this, you can actually, by using the head to tail method, you can see that OA plus AP is equal to OP, right? So let's just see what that means. So the vector A plus AP is equal to OP, right? So OP is equal to R. And basically we need to find AP. So AP is equal to R minus A, right? Similarly, if you look at this triangle over here, this lower triangle, by using the head to tail method, you can see that R or OP plus PB is equal to OB or B. So what that means is that R plus PB is equal to B, right? Now, since we need to find PB over here, PB is equal to B minus R, right? So we'll replace this AP over here with R minus A, right? So Q into R minus A is equal to, and this PB is equal to B minus R, so P into B minus R, right? Now let's expand this, multiply it. So Q R minus Q A is equal to P B minus P R, right? Now, since we need to find R, we'll take the terms with R in them on one side and everything else on the other side. So we have QR over here on the left hand side and PR over here on the right hand side, right? So we'll take them on one side and the rest on the other. So let's see. Just a second. Right. So QR plus PR is equal to PB plus QA, right? And let's take R common over here. So that just gives you R into Q plus P, is equal to PB plus QA, right? And you'll divide this on the other side because it's being multiplied on the left hand side, it'll be divided on the right hand side. So R is equal to PB plus QA over Q plus P. And that is how you got this. Funny, right? So yeah, that's the ratio formula proven. Now let's find the vector PQ in the equation form. Now let's see. We need to find PQ, the vector that runs from P to Q, in this form. Now, just to make things a bit easier for you to understand, say if you have this vector P. So to find the vector OP, what do? How do you find it? Well, since the position of O, or the origin, is 0, 0, 0, and the vector P is just 2, 3. To find OP, what do? Simple. You subtract, right? So you get 2 minus 0 and 3 minus 0, right? That just gives you 2, 3, right? The vector. Now, simply what you need to do here is to convert this into an equation form. You write the x value with I and the y value with j. So similarly for q, the vector OQ is equal to 6i minus 2j, right? Because 6 and minus 2. But these are with respect to the origin. We need to find PQ, and obviously PQ is equal to the vector OQ minus the vector OP. And just to clear it out how we got here, if you have this xy plane, the vector P is at 2, 3. So 2 on the x-axis, 3 on the y-axis. So let's just say this point is P, and Q is 6 on the x-axis and minus 2 on the y-axis. So this is Q, and this is the vector OP, this is the vector OQ, and this is the vector PQ, right? So as you can see, this is OP, this is PQ. So the vector PQ is equal to OP minus OQ. So this is how we got here. Now, this is what happened, right? Because OQ minus OP is equal to 2i plus 3j, which is OQ, 2i plus 3j, minus OP, which is, just a second, I mixed that up a little. Just a second. OQ is equal to 6i minus 2j, so 6i minus 2j minus OP, which is 2i plus 3j. Obviously, the terms with I will be subtracted and the terms with j will be subtracted. So 6 minus 2i and minus 2 minus 3j. That gives you 4i minus 5j. And in the non-equation form, this can be written down like this: 4 and minus 5. Okay? And similarly, in this question, you use the same technique. OQ minus OP, and that just gives you minus 1 minus 0i, because the x values of q is minus 1 and the x value of p is 0. And minus 6 minus 5j. Minus 6 is the x value, y value of q, and 5 is the y value of p. So this is the final answer in equation form. And again, in the non-equation form, this can be written down like minus 1 and minus 11. Now let's find the vector from point A to the origin. Now, find the vector from point A to the origin, and this is the vector given to us. A vector going from A to B, and the vector is equal to 4i minus 2j, right? And B is at the point minus 2, minus 5. Okay? So, here's the thing. AB is equal to 4i minus 2j. As you know, AB is equal to the vector OB, or the position vector of B, to the vector OA, or the position vector of A, right? So OB minus OA is equal to AB. B is given to us, so obviously OB is equal to minus 2i plus 5j. Okay? So AB minus OB, when you take OB to the other side, it becomes negative. AB minus OB is equal to negative OA. Negative OA is basically the negative vector of AO. So you can basically convert minus OA into positive AO because it's just the directions being opposed. Obviously, a vector going from OA, the negative of it will be in the opposite direction, going from A to O. So that is what we have to find. AO. So AB minus OB is equal to AO. We already have AB and we already have OB, which is this, right? We just subtract them. So 4i minus 2i minus 2i plus 5j, right? So this is the result. 6i minus 7j. Now let's find a unit vector, right? It says that we have to find the unit vector in the direction of the vector given below. So vector v is equal to 2i minus j, right? So as you remember, just the formula, if you have a vector u, then the unit vector of the vector u is equal to the vector u divided by its magnitude, right? Same will apply over here. We have the vector v, 2i minus j. Now we find its magnitude, and you find the magnitude by squaring the x term and then squaring the y term and then adding them up and then taking the under root of the result. So the x term is 2 and the y term is minus 1, right? Because this is minus j is basically equal to minus 1j. So 2 square plus minus 1 square will give you 4 plus 1 under root. So that just means under root 5. And that is basically the magnitude of the vector v, right? So the unit vector v, the unit vector of v is equal to the vector v divided by its unit vector. So 2i minus j divided by under root 5. And you can basically just separate the 2i and minus j. So this becomes 2 over under root 5i minus 1 over under root 5j, right? And so this, if you take the magnitude of this vector over here, that'll give you 1 because the magnitude of unit vector is 1. Now we have another vector. We'll apply the same method. Find the magnitude of this vector. That gives you 1. And so basically, the unit vector is the original vector divided by the magnitude. So what this basically means is that this original vector given to you is a unit vector as well. And how did you do not need to go through all this, whatever we've done over here. Because once you find out that the magnitude of this vector is 1, that automatically means that it is a unit vector, because unit vector is a vector with a magnitude of 1, right? Now let's find the coordinates of a point. If A, B, and C are these points, respectively. Use vectors to find the coordinates of point D if ABCD is a parallelogram. Now, if it's a parallelogram, that makes things a bit easier, right? So, let's just assume that the coordinates of D are X and Y, right? So, this is the parallelogram. This is point A, this is point B, this is point C, and this is point D. Now, since it's a parallelogram, that means that this side and this side are parallel, this side and this side are parallel. So, you can see that the vector AB is equal to the vector DC, right? Because they're parallel. So what you can do now is just equate both of them. Now, to find the vector AB in equation form, AB is equal to OB minus OA, right? And as you know that the equation of OB is basically this: 4i plus 0j minus OA. OA is this. So minus 2i minus 4j. Once you equate that, you get 4 minus 2i and plus 0 plus 4j, which is equal to 2i plus 4j, right? Now, that's AB. So 2i and plus 4j. Now we need to find DC. We know that DC is equal to OC minus OD. Now we already know what OC is. It's this, 1 and 6. So I plus 6j. We took the arbitrary values of x and y to denote D. So OD is basically equal to xi plus yj, right? So this basically equates to 1 minus xi plus 6 minus yj. And once you equate that, you get this. 2 is equal to 1 minus x, right? Because look at this. The value for I on the left hand side is 2, and the value of I on the right hand side is 1 minus x. So 2 is equal to 1 minus x, and similarly 4 is equal to 6 minus y. Because you treat the values of I and j completely separately. Because one is on the x-axis, the I, and one is on the y-axis, the j values, right? So once you equate them, this is what you get. Now you can solve them. So x is equal to 1 minus 2, which is equal to minus 1, and y is equal to 6 minus 4, which is 2. So the coordinates of C are minus 1 and 2. Sorry, the coordinates of D. We need to find the coordinates D, so they are minus 1, 2. Now, we need to show that the line, the vector AB, is parallel to the vector CD. So we have the positions of the point A, B, C, and D. So the position vector of A is 2i minus j. The position vector of B, the position vector of A is 2i minus j plus k. The position vector of B is 3i plus j. The position vector of C is 2i plus 4j minus 2k. And the position vector of D is minus I plus minus 2j plus k. So we need to show that the vector AB is parallel to the vector CD. Now, the vector AB is obviously equal to OB minus OA. We know that the vector OB is this, 3i plus j. And we know that the vector OA is this, 2i minus j plus k. Now simply just subtract OA from OB. So the x component of B minus the x component of A with I, the y component of B plus the y component of A into J, and the k component, the z component of B minus the z component of A into K. And that gives you this. So the vector AB is equal to I plus 2j minus k. Now, remember that two vectors are parallel if they are scalar multiples of each other. Right? So let's find CD and let's see if it is a scalar multiple of AB. So CD is the position vector of D minus the position vector of C, right? And again, from the equation, just like we did AB, we just separate them into the three x's, I, j, k, and this is what you get. Now, as you remember that the vector AB was equal to I plus 2j minus k. And CD, if you take minus 3 common in all three terms, you get minus 3 into I plus 2j minus k. So CD is equal to minus 3AB. So it is indeed a scalar multiple. So CD is indeed a scalar multiple of AB. Hence, AB is parallel to CD. Now let's find the position vector using the ratio formula. So we have to find the position vector of the point of division, right, of the line segments using this formula, right? And what are the pair of points that will be divided? So the point C with this position vector and the point D with this position vector. And the line CD, the vector CD, is divided by this ratio, 4:3, right? So we have the position vector for C, which is C. Let's just denote it like this. And the position vector for D, we can denote it like this, right? Now, here's the thing. This is the ratio that they are divided by. So this 4 we'll call P, and let's call this one Q. Okay, so this Q over here, that will become, oh, in this case, let's just take this example over here. Q is equal to 3, P is equal to 4, and A is equal to C, and B is equal to D. Okay, so that's that clarified. Now let's just plug in the values. We have to find R. So this is the formula, and so we found out Q to be equal to 3, right? And A was equal to the position vector of C, so that's this. And we found P to be 4 and this to be the position vector of D. So now, and this is the denominator, Q plus P. So Q plus P was equal to 4 plus 3, obviously. And once you actually expand and do all the calculations, you'll find out that this is the result. So this is the position vector of the point dividing the line CD by the ratio of 4 by 3. Simple. This formula is really, it's just something that makes your life very easy. You just need to know how to apply it. Now let's find the midpoints of the sides of quadrilaterals. So we need to prove that the line segment joining the midpoints of the sides of a quadrilateral are taken in the order form of a parallelogram. So here it is. Basically what this means is that this quadrilateral ABCD, right? H, this one, it says here that let ABCD be the point, the position vectors of the vertices ABCD. So the ends, so this is A, this is B, this is C, and this is D, right? So we let E, we need to prove, basically what the question asks, that we need to prove that the line segments joining the midpoints of the sides of the quadrilateral taken in order to form a parallelogram, right? We need to prove that when you join the midpoints of each of the sides of the quadrilateral that is given to us, it forms a parallelogram. Okay, so we just draw this out as, you can really just draw anything, but we let E be the midpoint of the line AB. We let H be the midpoint of the vector AB, so the vector AD. G is the midpoint of DC, and F is the midpoint of BC, right? So we have 4 midpoints, and it says that when you join these midpoints, it gives you this parallelogram called EHGF, or like whatever, like FGH, and like all this, right? So here's the thing. In a parallelogram, obviously, this side and this side, the opposite sides are parallel, right? So we need to prove that EH is equal to FG and GH is equal to FE. So how do we do that? Well, we use the same ratio formula. It says here that let E be the midpoint of AB. So OE is equal to the vector A, the position vector of A, plus the position vector of B over 2. How did we find this? How did we find this? Well, you remember that the ratio formula said that R, which is obviously the midpoint in this case, because we need to find the position vectors of, we need the position vector of E, which is OE over here. R is equal to QA plus PB over Q plus B. Now in this case, since it's the midpoint, the ratio is equal to 2:2, the ratio of Q and P. So that will basically mean that 2A plus 2B is equal to Q plus B, which is 2 plus 2, which is equal to 4. So when you take 2 common over here, that means it's 2A plus B over 4. Now you can cancel this out and this becomes 2. So that just leaves you with A plus B over 2. And that is how you got this equation over here. Now when you apply the same rule on all of the other side, you find out that OF, which is the position vector of this F over here, that is equal to B plus C over 2, because it's between B and C, right? And for G, you guessed it, it's C plus D over 2. And for H, it's A plus D over 2. Okay, now that you have this information, you know that FE is equal to OE minus OF. Obviously, because, well, that's just how it is. If you draw out the whole thing, you can use the head to tail method to see that FE is equal to OE minus OF. Now, let's just see. FE, right? FE, and when you take this to the origin side, let's say that this is the origin. Oops. If you say that this is the origin, that means that this is OE and this is OF, and this is OE, this is OF, and that means that OF plus FE is equal to OE. So OF plus FE is equal to OE, which means that FE is equal to OE minus OF, and that's how you prove that, right? And similarly, you can use the same head to tail method for all of the other sides. So you see that FE and GH give you the same result, AA minus C over 2, which means that both those two sides are parallel. And similarly for FG and EH, when you do all the calculations, you find out that they are parallel as well, which means that two sides are parallel, the two opposing sides, which means that this is indeed a parallelogram, right? Because when the two opposing sides are parallel in a four-sided quadrilateral, that means that it is a parallelogram.
Now let's discuss some properties of vectors. So vectors, both in the plane and in space, so 2D and 3D vectors, have the following properties. Now let's just say U, V, and W are three vectors in the plane or space, and let A and B be any real number. So basically A and B are constants, right? So they're just scalars. Then they have the following properties. So when you add two vectors, let's say you add U and V, that's equal to if you add V and U. That's just simple. And this is called the commutative property. Now, if you first add U and V, the vectors U and V, and then you add another vector W into the sum, that's equivalent or equal to as if you first add V and W and then you add U to the sum, right? And this is called the associative property. Now, if you have a vector U and you add it to its negative vector, so negative U or -1 into U, that's equivalent to as if you obviously subtract U from U, right? And when you basically add negative U to positive U, that gives you a zero vector. And this is called the inverse for vector addition. This, not this really, this is the inverse of this. And when you add them up, it gives you a zero vector. Now, if you have a scalar A and you multiply that into the sum of vectors V and W, that's equivalent to as if you basically multiply the scalar A with V separately and you multiply the same scalar A with W separately and you add them up. These two things will give you the same result, and this is called the distributive property. Now, if you have a scalar A and a scalar b, right? If you multiply the scalar b with the vector u, the result that you get over here, if you multiply a with that result, it's equivalent to as if you basically multiply the two scalars first, and that result is being multiplied with the vector u. And this is called scalar multiplication. So just to make life a bit easier, instead of just doing all the calculation on the vector with one scalar and then multiplying another scalar with that result, simply just multiply the two scalars and do the hard part, the multiplication with the vector, after that. Let's find the vector AB and sums of vector. So this basically is the use of the properties of vectors that we discussed earlier, right? So it says that we have the point A at 2, 5. So 2 on the x-axis, 5 on the y-axis, B on -1, 1, and C on 2, -6. So we need to find the vector AB. So that's pretty simple, right? First, you must remember this, right? AB is equal to OB minus OA. OB is the position vector of B, OA is the position vector of A. So the point A is 2, 5. So obviously, as we have discussed many times earlier, the position vector of A, OA, that goes from the origin to A, is 2i plus 5j, because it's 2 on the x-axis and 5 on the y-axis. Now, the point B is at -1 and it's at +1, right? So obviously, its position vector OB will be at -i plus j because it's at -1x plus 1y. And the point C is at 2 -6, so OC is obviously 2i minus 6j. Now it says that we have to find AB, right? So AB is equal to OB minus OA. And you can verify this by using the triangle method of vector addition. Now, AB is equal to -i plus j minus 2i plus 5j. Obviously, you must remember that the I components are added separately and the j components are added separately, or in this case, subtracted. So yeah, this is what you get. -3i minus 4j, right? That's AB. Now, it says that we have to find 2CB minus CA. So here's what we'll do. This is actually 2CB minus 2CA. They forgot the 2 here. Now, obviously, as you remember, in the vector properties that we discussed, you can take this 2 and this 2 common outside of a bracket like this. 2 common, and in the bracket, you're subtracting the 2 vectors, CB and CA. Now, as you know, CB is equal to OB minus OC, the position vector of B minus the position vector of C, and CA, that's right, the position vector of A minus the position vector of C. Okay, now we already found these values earlier, but to make things even simpler for us, first expand this, and this is what you get: OB minus OC minus OA plus OC. This OC and this OC can be cancelled out because this one is negative and this one is positive, and so you're left with 2OB minus OA, right? And we found OB to be this and OA to be this, and now that makes things a lot simpler for us. The final result is this. Now let's find a vector whose magnitude is given. It says that we have to find a vector whose magnitude is 4, right? and it is parallel to this vector. Now, we need to find the actual vector. So let's say that vector A is equal to this parallel vector, right? And let's find the magnitude of A. Obviously, the magnitude of A is basically the square of this term, and this term, the sums of the squares of these terms, whole under root. So you get under root 49, which is equal to 7. So that's the magnitude of the vector that is parallel to the vector we actually have to find. And the magnitude of that vector is 4. That's already given to us. That simplifies this a bit. So the unit vector parallel to A, right? The unit vector parallel to A, so this vector is equal to the actual vector A divided by its magnitude. We know the magnitude is 7, and the actual vector is already given to us in the question. So to find the required vector, you simply have to multiply the magnitude of that vector with the unit vector A, which is this, right? So basically, let's just say that the vector that we had to find was vector B. So B is equal to the magnitude of B into the unit vector A, because but the condition is that A is parallel to B. So basically, the unit vector of A and the unit vector of B are same. Since they're both parallel, the only difference is the magnitude. The magnitude of A is equal to 7, and the magnitude of B is equal to 4. But the magnitude of the unit vector A is equal to 1, obviously, because it's a unit vector. And the magnitude of unit vector B is also equal to 1. But here's the thing. All of these have the same direction because they're parallel, right? Same direction. So the only difference between A and B is the magnitude. But since everything about the unit vector is the same, so the unit vector A is equal to the unit vector of B. Which is why this is basically equal to B into B, the unit vector B, right? So I hope that simplifies it down a bit. And yeah. Now, this is one of the most important concepts in the whole discussion of vectors, and that's the scalar product of two vectors, also known as the dot product. So here's the thing. The scalar product is basically, first let's discuss what the concept really is. If you have two non-zero vectors, u and v, right, in the plane or in space, and they have the same initial point, which means that basically, let's say this is the vector u. Since this is the initial point of u, the second vector must start from this same exact initial point, right? So this is vector v. They have the same initial point. The dot product of u and v will be written like this, but how is it defined? So u dot v is equal to the magnitude of u multiplied with the magnitude of v into cos theta. What is theta? It's the angle, this angle, between the vectors u and v that we're taking the dot product of, right? And the theta must lie between pi and 0, or in terms of degrees between 0 and 180 degrees, right? Now, and another reason why that is because if you have this as the vector v, again, this is v, and let's say that this is the vector u. Now, this is still an angle between them, but let's say this is vector v, and let's say this is vector u. You'll not take this as theta. No, that's not correct. This is theta, which is why theta must lie between pi and 0. Because once it exceeds this 180 degree mark, you'll take the short angle. So that's practically useless, right? It will always lie between 0 and pi. Now, the definition of perpendicular or orthogonal vectors. The two vectors u and v are orthogonal or perpendicular if and only if u dot v is equal to 0. How will it be 0? Remember that the dot product or the inner product or the scalar product, they all mean the same thing, by the way. They're the same, right? So I into I is equal to j into j is equal to k into k, which is equal to 1, which basically means anything on the x-axis being multiplied with anything on the x-axis again is basically in the same direction. So let's say this is the vector u, and the vector v lies on this same exact, is parallel to the vector u, right? So what is the angle between them? It's 0. And what that means is that it's basically the dot product of u and v is equal to u, the magnitude of u, into the magnitude of v, into cos of 0. And remember that the cos of 0 is equal to 1, right? But in this case, it says I into I, which means 1 on the x-axis and 1 on the x-axis. When they're taking the dot product, their magnitude is also the same. So that's basically equal to, in the case where both of them are equal, not this case really, in this case, 1i into 1i. So the same vector of 1 being taking a dot product of 1 with itself is basically equal to 1, the magnitude of 1, 1 cos 0, which is equal to basically 1 into 1 into 1, which is equal to 1. And same goes for j into j, k into k, right? They're parallel vectors of one magnitude literally being multiplied with each other in the same direction. The I and I are in the x-axis, j and j are in the y-axis, k and k are in the z-axis. So they'll all give you the same result of 1, right? So we'll apply the same logic to perpendicular vectors. Remember that I into j, which basically means, let's just make a, whoops, forget the drawing, but right, let's just say this is a 3D plane, right? Say that this is the x-axis, this is the y-axis, and this is the z-axis. It says the I into j is equal to 0. Why is it equal to 0? Because let's just say this, we have a vector on this, let's call it, this is the vector I, and on j we have this vector j, right? They have an angle of 90 degrees between them, right? Because if you look at it from a bird's eye view, it looks like this, right? X, y, and this is the 90-degree angle. So the angle between I and j is 90 degree, and cos 90 is equal to 0, which means that any term being multiplied with this is equal to 0, in which case I dot j is equal to magnitude of I into magnitude of j into 0, which is equal to 0. Same goes for j and k, right? Because the y-axis and the z-axis are again at 90 degrees from each other. So let's just say this is k. So again, at 90 degrees, the cos term, cos 90, becomes 0. So this is also equal to 0. And the z-axis and the x-axis, or k and y, are also perpendicular to each other at 90 degrees. So that is also equal to 0. And that is the concept of orthogonal vectors. And the scalar product is commutative, right? So u dot v is equal to v dot u. We've discussed this earlier. Now, the properties of a dot product. We let u, v, and w be vectors, right? And let c be a real number or a scalar quantity, right? So u dot v is equal to 0 if the vector u is equal to 0 and the vector v is equal to 0. That's pretty self-explanatory, right? Because in this case, since u is equal to 0, it's a 0 vector. V is also equal to 0, it's a 0 vector. So obviously 0 into 0, it has no magnitude. This has no magnitude, right? Is equal to 0. And the magnitude of v is also equal to 0. So obviously 0 into cos of any number is always equal to 0, which is why we have the 0. Now, again, u dot v is equal to v dot u, the commutative property, simple. And we have the distributive property again, which says that v plus w, the vector, the sum of v and w, right? The result of the sum of the vectors v and w being multiplied then with the vector u is equal to, as if you basically multiply u and v, then you multiply u and w, and then, right, u and v, u and w, and then you add the results up, right? So this is the distributive property, basic math really. So now we are doing multiplying the vector u with the scalar c, and the result of this multiplication is then multiplied with v, right? This is equal to, as if you first multiply the vector u and the vector v, taking the dot product of u and v, and then multiplying the result of that dot product with the scalar c, right? Now let's find the angle between two vectors. Now, you can find the angle between two vectors by taking the dot product of the two vectors. As you know, vector u dot vector v is equal to the magnitude of u multiplied with the magnitude of v and the angle, the cosine of the angle between the two vectors, right? So once you take these two terms, the magnitude of u and v, to the left hand side, it goes to the denominator, right? So cosine of theta is equal to u dot v divided by the magnitude of u divided by the magnitude of v. And that's how you can really find the theta, because you can find theta by just taking the cosine inverse of u dot v over magnitude of u into magnitude of v, right? So if you have a vector u, let's say it's a1i plus b1j plus c1k, and v is a2i plus b2j plus c2k, then u dot v is equal to a1 into A2 plus B1 into B2 plus C1 into C2. And as you know that the magnitude of U is equal to A1 square plus B1 square plus C1 square whole under root, right? And similarly, the magnitude of V is equal to the under root of A2 square plus B2 square plus C2 square. This is really simple procedure. So once you join them all up, you can see that U dot V is equal to A1 A2 plus B1 B2 plus C1 C2, and divide that by U, the magnitude of U, into the magnitude of V, which is this. This is the magnitude of U, and this is the magnitude of V. And then you can take the cosine inverse to find theta, the angle between U and V. Here's an example. It says that we have to find the cosine of the angle theta between U and V. U is given as 3i plus j minus k. V is given as 2i minus j plus k, right? So first we find U dot V, which is basically just 3 into 2 plus 1 into minus 1, right? Plus minus 1 into plus 1. So 3 into 2 plus 1 into minus 1 plus minus 1 into 1. And that gives you 4. You found U dot V. Now you need to find the magnitude of U multiplied with the magnitude of V. So let's first find the magnitude of U, which is just 3 square plus 1 square plus minus 1 whole square, whole under root, right? And that basically just gives you under root 11. And for V, 2 square plus negative 1 square plus 1 square. And that gives you under root 6. Now you can find cosine of theta, which is equal to U dot V, which we found. And also we found the magnitude of U, and we also found the magnitude of V. So that gives you 4 divided by under root 6 into under root 11. And once you take the cosine inverse of this whole term, you can find theta, right? Now let's see how you can calculate a projection of one vector along another. So it says here that we have to calculate the projection of vector A along vector B, and we also have to calculate the projection of vector B along vector A. Now in layman terms, let's see what projection really is. Now the name really gives away itself, but this is what it is. Let's say that this here is vector A and this here is vector B. Now the projection of vector A along vector B would be this, the shadow that vector A casts along vector B. So this would be, let's just call it A prime, the projection. And a simple way to calculate this is to first take the dot product of A and B and divide it by the vector that the projection is being taken along. So in the first example, this one here, it says there that we have to find A along B. So you take the magnitude of vector B in the denominator, right? Because that is the vector that it is being taken along, right? So, and obviously in the second case, you would again take the same A dot B in the numerator, but you'll divide it by the magnitude of vector A, because that's what the projection is being taken along. So, and you can see that if A makes a 90-degree angle with B, say this is B, right? This is A and this is B. Then you can see that it has no projection, and that can be proven because in this case A dot B would be equal to 0. This is a very beautiful example. Now it says here that A is equal to I minus K, so plus 1 on the x-axis and negative 1 on the z-axis, and B is J plus K, right? So A dot B, you first obviously have to find A dot B. Now that would just be 1 into 0 plus 0 into 1 plus -1 into 1. And that gives you -1. You found A dot B. Now, in the first case where you have to find A along B, you need to find the magnitude of B. And in the second example, when it's B along A, you have to find the magnitude of A. So let's just calculate the magnitude of both A and B. So the magnitude of A is simply 1 square plus 0 square plus -1 square, which will just become the under root 2. And the magnitude of B will also be under root 2. Now the projection of A along B is obviously equal to A dot B over the magnitude of B, which is equal to -1 over under root 2, right? Because A dot B was equal to -1 and the magnitude of B is -2, is under root 2. And similarly for B along A, it's the same, -1 divided by under root 2. So this is how you calculate projections, a very simple concept, and I hope that helped. Now let's see how you can find a real number when two vectors are perpendicular. It says here to find the real number alpha so that the two vectors u and v are perpendicular. It says that u is equal to 2 alpha I plus j plus minus k, v is equal to I plus alpha j plus 4k. How will you find this alpha value when the two vectors u and v are perpendicular? Now, some of you may have already guessed it, but to some you may be a little confused as to how you can actually find alpha, because for that you need to have a whole equation where alpha is the only variable, right? So there must be something, and the key is this word here. Now such clues will be given to you. Not everything is handed to you in a silver plate. It says here that both u and v are perpendicular. So what that means is that the dot product of u and v is equal to 0. And as some of you, in case you don't know, when the angle between u and v is 90 degrees, since it's perpendicular, that means that the cosine of the angle between them, which is cosine of 90, is equal to 0, right? And since u dot v is equal to the magnitude of u into the magnitude of v and the cosine between them, which is 90, that means this entire term becomes 0. So now you can just take the dot product of u and v and equate it to 0. And once you take the dot product, you find out that it turns out that 3 alpha minus 4 is equal to 0, which means that 3 alpha is equal to 4. And so once you take this 3 to the denominator on the right hand side, alpha turns out to be 4 over 3. That's really how simple this question is. You just have to look for particular clues, which in this case is the perpendicular nature of u and v. Now, here's a more difficult type of example. We have to show that the midpoint of a hypotenuse is equidistant from its vertices, right? So this here is an example. Now you have this line AB as the hypotenuse of this triangle OBA, right? Now we need to show that the midpoint of a hypotenuse of a right angle triangle is equidistant from its vertices, and the midpoint of the hypotenuse is this C over here, right? So it says that it is equidistant from its vertices, which are these here. We need to prove it. So we let the triangle AOB be a right angle triangle, and let C, this here, be the midpoint of the hypotenuse AB, as I mentioned earlier. And we know that the point A is A0 because it is on the same level as the origin on the y-axis, but it has a different x point, which we'll call A, right? So A is at these points, A0, sorry, and so the vector, the position vector of A is OA, which is equal to AI plus 0j, obviously, because A on the x-axis and 0 on the y-axis. So it is basically just equal to AI, right? And similarly for B, it is on the same level as the origin on the x-axis, so it has 0 on the x coordinate, but it has this lowercase b on the y coordinate because it doesn't have a 0 y coordinate. So we know that point B is 0b, so the position vector of the point B can be written down as 0i plus bj, obviously. So we'll just say that it is equal to bj, because obviously the I term becomes 0. And it says that the point C is the midpoint of AB, right? So obviously, since it is the midpoint of AB, this on the y-axis, it will lie at the halfway point between OB, b by 2. And at the x point, it would lie at the midway point between OA. So that becomes a by 2. Now, OC, the vector between O and C, the position vector of C, is equal to a2i plus b2j, obviously, because these are the coordinates, a by 2 and b by 2. We have to show that the magnitude of the position vector OC is equal to the magnitude of the position vector AC, which is equal to the magnitude of CB, right? And just to explain why that is, because this is OC, this is OA, and this is OC. The equidistance basically means that this triangle OCA is an equilateral triangle. And we need to prove that. So AC, the vector AC is this vector over here, AC, right? That is equal to OC minus OA. Simple. We've discussed this many times earlier, why that is. AC is equal to OC minus OA. So AC is equal to minus A by 2i plus B by 2j. We found AC. Now, we need to find CB, which is equal to OB minus OC, obviously. And that turns out to be minus A by 2 plus B by 2j, right? And OC, the magnitude of OC is equal to A by 2 whole square plus B by 2 whole square whole under root. And that turns out to be A square over 4 plus B square over 4 whole under root, right? So we found the magnitude of OC, which is simplified. Turns out to be this. Now, AC is negative A by 2 whole square plus B by 2 whole square whole under root. And that turns out to be exactly the same as the magnitude of OC. So we got that covered as well. Now we need to find CB, and again that turns out to be exactly equal to AC and OC, the magnitude of OC and AC, right? So this, and this are equal, right? So the magnitude of OC, the magnitude of AC, and the magnitude of CB turn out to be equal to A square plus B square whole under root divided by 2. And that's how you prove that the midpoint of the hypotenuse of the right angle triangle is equidistant from its vertices. Now let's discuss the definition of a vector, or the cross product of two vectors, and we'll also discuss their properties and what parallel vectors are in this definition. So now let U and V be two vectors, and the cross product of the two vectors is basically the magnitude of U multiplied with the magnitude of V into sine theta into n. Now what is this n? N is a unit vector perpendicular to the plane of U and V. Now it's very, very important to understand this, because once you understand this, everything becomes clear. Now a very fundamental difference between cross product, the resultant of a cross product between two vectors, and the resultant of a the dot product of two vectors and the resultant of a cross product of two vectors have a fundamental difference, that a dot product is basically gives you a scalar value, and the cross product basically gives you vector value, right? So it has a direction, and that direction comes from this. Okay, and because obviously if you just take the magnitude of u, the magnitude of v, and the sine of the angle between them, that just gives you one value, which is a scalar, just like in the dot product, right? But since the cross product gives you a vector value, you need to multiply it with something to give you a vector value, and that is this n right here. And it is perpendicular. This n is the unit vector perpendicular to the plane of u and v, right? But it's also very important to understand why. Because you see, if you have a three-dimensional plane over here, this will really help you understand this later on. If you have this over here, say this is the x-axis, this is the y-axis, and this is the z-axis, right? Now, the dot product between x and y, this can be found by the right-hand rule. What you do is you curl up your right hand with the thumb pointing out, right? Now, the four fingers, except for the thumb, the four fingers apart from the thumb, if it says that you have to find x cross y, right? Sorry, x cross y, right? That will give you what? Well, it gives you the direction that the thumb is pointing towards. So if you it says that x cross y, now what you have to do is you have to curl the four fingers apart from the thumb from x towards y, right? And then you'll see that once you do that, it gives you the thumb points towards the positive z-axis. However, if it said y cross x, well, you'll curl your fingers in the direction y towards x, and that will tell you that once you do that, the thumb that is pointing out, it will point towards the negative z-axis, which means that will give you negative z. And this is a very important concept to understand. Once you get the hang of this, this becomes a piece of cake for everyone. You just try this out a few times. Try this between z and y, when it's z cross y cross z, x cross z, z cross x, and you'll understand later on. So u cross v is equal to the magnitude of u multiplied with the magnitude of v, sine theta, the theta is the angle between u and v, into this n, which is the unit vector perpendicular to the plane of u and v, right? Now n can be found by taking the cross product of u and v and the magnitude of the cross product of u and v, right? So this is a bit different. So sine theta you can just find by u cross v over the magnitude of u into the magnitude of v into this vector n. Basically from this can be just found from this first equation, right? And sine theta can also be found by this, the magnitude of u cross v over the magnitude of u into the magnitude of v. So now you have two formulas to help you find sine theta. But again, the most important thing is this concept over here. By using your right hand, you can find the direction of the vector n. Now, properties of cross vectors, again, u cross v is equal to 0 if u is equal to 0 and v is equal to, pretty self-explanatory, right? Now, u cross v is equal to negative v into u, right? And
that again can be explained by the right hand rule, right? Because if you see over here in the right hand rule, if instead of x, when you remember that x cross y, that means going from x to y with the thumb pointing towards the positive z, that just basically means that if you take negative x, if you take the negative of x, that means it is the negative x-axis. So from negative x-axis towards y, which is this direction over here, that is basically the same as y cross x, because it's going like this, right? The clockwise direction if you look from above, which is why my negative x into y is equal to wait just a second, let me just erase this off. So negative x cross y is equal to y cross x, which is equal to negative z, and that is what this property is. U cross v is equal to negative v cross u. And the third property is the distributive property, which says that u cross the sum of v and w is equal to, as if you basically take the cross product of u and v and add that to the cross product of u and w, right? And now here is another property which says that if you take the scalar multiple of v with k as the scalar, and then you take the cross product of their sum with u, that is basically equal to as if you take the scalar multiple of k with u, and then the result of that, the cross product with v. And all of this is also equal to as if you take the cross product of u and v and then multiply the result with the scalar k. And the fifth property is that u cross u is equal to 0. Why? Because u and u have an angle of 0 between them. So theta is equal to 0, which means that sine theta is equal to sine 0, which is equal to, you guessed it, 0. Now let's discuss the parallel vectors. If u and v are parallel vectors, that means that theta is equal to 0 and sine theta is also equal to 0. So u cross v, this is the fourth property that we discussed earlier. U cross v is obviously equal to u into v, in the magnitude of u into the magnitude of v, into sine theta into the vector n, which is parallel to u and v, right? And you know now how to find the direction of that unit vector. So u cross v is equal to 0, or v cross u is equal to 0 when they are parallel, because theta is equal to 0 between them. The angle between the two vectors u and v is equal to 0 when they are parallel, obviously. But so sine theta is equal to 0, or where u cross v is equal to 0 in three conditions: when sine theta is equal to 0, u is equal to 0, the magnitude of u is equal to 0, or the magnitude of v is equal to 0. If sine theta is equal to 0, theta is equal to 0 or 180, right? Because parallel vectors can have opposite directions as well. So the angle between them can either be 0 or 180. But again, it's the same thing. You need sine theta to be equal to 0. So sine 180 is also equal to 0, right? Because that's, if you just calculate sine 180, it gives you 0. So this, when sine theta is equal to 0, that means that u and v are parallel. Simple rule. If u is equal to 0 or v is equal to 0, then since the 0 vector has no specific direction, we adopt the convention that vector is parallel to every vector, right? 0 vector is basically nothing, so it's basically parallel to everything. So that's just a very simple explanation. And but further, this is very important to remember, this particular point. Since it has no specific direction, the 0 vector has no specific direction, that means that it is parallel to every vector. And so yeah, these are the two rules, and that's just it.
Now let's compute the cross product. Let's see how we can compute a cross product. And it says that we have to compute the cross product of A and B. So A cross B and B cross A. Now remember, in dot products, A dot B, is equal to B dot A. But so that's not the case for cross products. A cross B is not equal to B cross A because the direction of the resultant vector is different. So it says that we have to check the answer by showing that each A and B is perpendicular to A cross B and B cross A. As you know, the resultant vector of a cross product is perpendicular to the plane of the vectors that the cross product is being taken of. So the resultant vector of A cross B will basically be perpendicular to the plane AB. And so like if this is vector A and this is vector B, that means that the cross product of these two vectors will either be outside of this page or into the page, because only those two options are perpendicular to A and B, right? So now we have A as 2i plus j minus k and B as I minus j plus k. Two vectors given to us. Now we know that if A is equal to this and B is equal to this, then A cross B is basically found by using this method. Now what is this really? Well, this is a very simple way of calculating the cross product, right? Now here's the thing. Basically, in the first row you write down I, j and k, okay, because those are the two common things in both of the vectors. Now in the second row you write down the coefficients of A, so, and under the correct column. So in the case of A1 is the coefficient of I, so it comes under the I column, right? A2 is the coefficient of J, so it comes under the J column. A3 is the coefficient of K, so it comes under the K column. And in the third row you write down the same way for the coefficients of B. So B1 comes under the I column because it's the coefficient of I in B, and same for B2 and B3. Now what do you do once you make this? Well, you write down the actual coefficients, obviously, as they are given in the question, and then you expand. And how do you do that? Well, first off, you basically, like, if you first take the first column, right? So you cancel out, you take this I, and you basically cancel out its column, and you cancel out its row, right? And then you write down I, and then you multiply it with the product of these two and these two, the basically the diagonals that are remaining. So 1 into 1 is 1, and from that you basically subtract the product of the other diagonal, and minus 1 into 1 is, and minus 1 into minus 1 is 1. So basically that gives you 1 minus 1, right? And then basically for the second, in the case of J, now let's see what you do in the case of J, right? Let's just erase this. Okay, now the second step is to cut out the J column. So basically the row of J is the first row and the column of J is the second column. Now what remains are this term, this term, this term, and this term. Now the J term will have a negative sign because that's just convention, and basically it will now
be multiplied with the same rule, right? So 2 into 1 minus negative 1 into 1. So 2 into 1 minus negative 1 into 1, which basically gives you 2 plus 3, right? Sorry, 2 plus 1. And that's exactly what you've done here. Now for k, here's what you do. Again, you cancel out its column and you cancel out its row. And these are the 4 terms remaining, right? And j was negative, so k will be positive. So basically now, again, in the brackets, 2 into negative 1 minus 1 into 1. So 2 into negative 1 minus 1 into 1, which basically gives you minus 2 minus 1. And that's what you have here. So this is just a very quick way of basically, so the only thing that you have to remember here is that I is positive, j is negative, and k is positive. This is just the convention that we follow, right? And the only case where j would become positive is if the the term that it's being multiplied with is also negative, right? That's just simple maths. So now a cross b basically gives you minus 3j minus 3k once you calculate this entire thing, right? And b cross a, as you know, is in the opposite direction of a cross b, because obviously again, if you have this in the plane, and let's say this is a and this is b, and if you do a cross b, that would mean that the resultant vector is either into the page or outside of the page, right? So whatever result you get, the vector of b cross a will be in the exact opposite direction, which is why if you just basically negative a cross b is equal to b cross a. So that's why you get my 3j plus 3k instead of negative 3j into minus 3j minus 3k. And yeah, that's again the same rule, right? So now we need the verification. You see, if the vector a and the vector b are actually perpendicular to a cross b and b cross a. So let's just first take a in relation to a cross b. So what do? You take the dot product of a with a cross b, right? Because dot product is basically what the result of this is basically the magnitude of a, the magnitude of a cross b into cos of the angle between them, right? So the only way that this term becomes 0 is if this term is 0, which in this case it isn't, if this term is 0, which in this case again it isn't, and you're only left with this must be 0. And how is it 0? If theta is equal to 90 or it is perpendicular, in other words. So if this turns out to be 0, that means that a is indeed perpendicular to a cross b. And what do you know? It is indeed equal to 0. Now let's take b in relation to a cross b in the same way. Well, it turns out to be 0 as well. Now let's take a in relation to b cross a instead of a cross b. It gives you 0 again. And lastly, b in relation to b cross a, it gives you again 0. So that's how you prove that the original vectors are perpendicular to their cross product. So let's see how you can find the area of a parallelogram and a triangle using the cross product. So it says that we can represent a parallelogram like this. So u and v are adjacent vectors. This is u and this is v. and they are adjacent vectors, they're non-zero vectors, and the angle between them is theta, this angle right here. So now you can make a parallelogram shape by making these two lines. This line is parallel to the vector v, and this line is parallel to the vector u. And now you can basically see that this is the height of the parallelogram, and h, this height, is equal to the magnitude of u into sine theta, because sine theta, the sine of this angle, is equal to the opposite over the hypotenuse. The opposite is h, and the h, and the hypotenuse is u. And once you take u to the other side, you get this. H is equal to the magnitude of u into sine theta. Simple. And now the area of the parallelogram is equal to the base into the height. The height is u, magnitude of u into sine theta. And what is the base? It's v. So base into height is equal to uv sine theta. Now, remember this formula where u cross v is equal to the magnitude of u into the magnitude of v into sine theta n. Now, what was n equal to? N was equal to u cross v over u, magnitude of u into v into sine theta. And this term in the denominator can be written down as the magnitude of u cross v. So u cross v over the magnitude of u cross v, right? And since we're not concerned with this particular expression over here, because we're just here to find the area, you can basically write this particular term over here is equal to the denominator over here. So you can write that down like that. So the area of the parallelogram is equal to the magnitude of u cross v. Simple. Now, let's find the area of the triangle. And instead of going into complications, let's make this really simple. We have the same parallelogram again, right? We need to find the area of this triangle, right? What is the area of this triangle? Well, it is half of the area of the parallelogram, because this triangle and this triangle are the same. So basically the area of the triangle is half of the area of the parallelogram, which means that the area of the triangle is half of half of the magnitude of u cross v, or basically it can be written down as half of u, the magnitude of u into the magnitude of v into sine theta, which is basically just this angle over here. Now let's find the area of a parallelogram, and later on we'll also find the area of a triangle. We've discussed the basic theory behind this. Now let's do some questions, right? So it says that we have a parallelogram with these vertices A, B, C, and D, and we need to find the area. And again, you remember that the area of a parallelogram, is basically equal to the base cross product of with the height, right? That's the magnitude of base cross height. So AB is equal to OB minus OA. Again, just basic vectors. And that gives you this. You find AC. Now you take the cross product of AB and AC, right? Because that gives you the height. And once you take this cross product using the method that we discussed earlier, again, just a reminder of how to do that. You first cancel out, you first multiply I, you just write down I, and then you cancel out its column, you cancel out its row, and you take the diagonal multiples, you multiply the diagonals and subtract them from each other. So I into 2 multiplied by 1, so that gives you 2, minus 3 into negative 1, so that gives you plus 3 basically, right? And then you write down minus j, right? That's a very important thing to remember. J is negative, I is positive, j is negative, and k is positive. That's just the convention. And so Now let's just rub this off. And now let's take J. You cancel out its corresponding column, its corresponding row. Now you have 1, these terms remaining. Now you multiply the diagonal, so 1 into 1, that gives you 1 minus 3 into 2, so minus 6. And now plus k, right? Because only j is negative, I and k are positive in this convention. Now, when you take k, again, cancel out its corresponding row and column, right? Now you have this, this, and this, and this remaining. So 1 into negative 1, k into minus 1, minus 2 into 2, so minus 4, right? Now you have done the cross multiplication of AB and AC. And let me just clarify if I've written down this correctly. And yeah, indeed, this is what you get, right? And so this is the cross product of AB and AC. And as you know, the area of the parallelogram is basically the magnitude of AB cross AC. So you take its magnitude, and basically you end up with under root 75. Or basically 5 into under root 3 square units, because we do not know the units. They're not given to us. Now, let's find the area of a triangle. So, the points P, Q, and R make a triangle. Now, as you know, the area of a triangle is basically half of the parallelogram that it makes, right? So half of the cross product, half of the cross product of base and height, right? Oops, sorry, this is a bar because it's a cross product. Now, PQ is equal to OQ minus OP, very obvious. PR, that gives you this. Now, you have the base and you have the height, right? PQ and PR, you have the base and the height. Now simply, first you have to find the cross product of PQ and PR with the same method that we discussed earlier. Again, I'm not going to explain how this is done. It's fairly simple by this point. Now, expand R1 and you get the result of the cross product. Now what you have to do is simply take, multiply half with the magnitude of PQ cross PR. So half of the magnitude of this vector here. So in the end, that just results in 15 by 2 square units or 7.5 square units.
Now let's find a unit vector perpendicular to the plane. It says that we have to find a unit vector that is perpendicular, and once you see this, you already know that we'll use the cross product, and the plane contains A and B, vectors A and B, and we'll also have to find the sine of the angle between them, right? So some of you may have already guessed how you will find the sine, and everything is so related to each other, honestly. But let's see how we'll do this. So A is this vector here, and B is this vector here, and the plane that contains A and B, we need to find a unit vector perpendicular to that plane, right? So let's see. A vector perpendicular to A and B is obviously A cross B. As you know, a cross product always gives you a vector that is perpendicular to the two vectors that the cross product is being taken of, right? Because if you remember that that vector n is perpendicular to the two vectors. So let's take the cross product, and as you already remember how to take the cross product, and again, let me just remind you how to do that. The first term, I into 6 plus 9, how do you get it? You look at this I over here, you cancel out its column, you cancel out its row, and then you write down plus I, and then you multiply that with the product of these two vectors minus the product of these two vectors, and that gives you 6 plus 9. And the second one is minus j. So as you remember, now what you'll do is you'll do the same thing for j, but remember j is negative, not positive. I and k are positive, j is negative. Now again, cancel out the row of j, the column of j and the row of j, and then multiply 2 and negative 1, subtract that, and then from that subtract the product of minus 3 and 4. Always work in diagonals, and that gives you minus 2 plus 12, right? And same for k again, but again k is positive, right? So plus k, and into 6 plus 24. Again, how do you do that? Cancel out the column, cancel out the row, multiply 2 and 3 minus negative 6 into 4. That gives you 6 plus 24. Now that you've done that, you get this. So this is the cross product of a and b, right? Now you need to find the unit vector of this vector, right? So to find that, you first need to find the magnitude of a cross b. Well, you do that simply by taking the squares of all the terms and adding them up, and then taking the under root of the resultant value, and that gives you 35 in this case, right? So now what you need to do, the unit vector perpendicular to the plane containing a and b is a cross b over the magnitude of a cross b, right? And that gives you this. Now we need to find the sine of the angle. So first you need to find the magnitude of a, and the magnitude of the vector is, again, you need to take the squares of all the values of I, j, and k, take the under root, and that gives you 7. You need to do the same for b, right? And that gives you under root 26. So let theta be the angle between a and b, right? And we need to find the sine of the angle. So sine theta is equal to a cross b, the magnitude of a cross b, into ab sine theta. And you remember this by the formula, which was that a cross b is equal to the magnitude of a into the magnitude of b. Whoops, sorry, the magnitude of b. My mistake. The magnitude of a into the magnitude of b into sine theta, right? In case of the dot product, it was cos theta, but in this case it's sine theta. And we already found out the magnitude of a cross b, and we found out the magnitude of a, and like this, we found out the magnitude of b. Just divide them, and this is what you get. So the sine theta is equal to 5 over under root 26. Let's see how we can find if two vectors are perpendicular or parallel. Now remember the rule. If the dot product of two vectors is equal to 0, that means that the vectors are perpendicular, right? And again, the reason for that is because if the angle between them is 90, that means cos 90 is equal to 0, right? And cos 90 is basically used in the dot product, right? Now, in case to find if the two vectors are parallel, you take the cross product. And if the cross product is equal to 0, that means that the two vectors are parallel, right? And again, the reason for that is because in a parallel vectors, the angle between the two vectors is either 0 or 180, and you know that sine 180 is equal to 0 and sine 0 is also equal to 0, right? Now, this is one thing. In case of the dot product, there was another rule, right? The other rule was that if one vector, let's say the vector A, is a scalar multiple, and let's call that multiple k, of another vector b, that means that A and B are parallel, right? So here we have the rules. Now let's see. We've been given these three vectors, right? U, V, and W, and we need to find if these three are perpendicular or parallel to each other. Let's take U and V. To find out if U and V are perpendicular to each other, we will take the dot product and see if it is equal to 0. And in this case, it is not equal to 0. It is equal to -6, which means that the two vectors are not perpendicular. Similarly, to find out if they are parallel, we take the cross product, and that gives us this. And this is also not equal to 0, which means that u and v are not parallel either. Now, in case of w, as you can see, w is, if you take negative 3 common in this vector w, you find out that this vector here is equal to u. So w is equal to minus 3u, which means that w is a scalar multiple of u, which means that u and w are parallel. Now, v dot w, right? And again, if u and w are parallel, that already implies that they cannot be perpendicular. That's just how it is. So, v and w, v dot w, what does that give you? V dot w gives you 18, which means that v and w are not perpendicular to each other. And v and w cannot be written as scalar multiples of each other, so they are not parallel either. So the only result that we got is that u and w are parallel to each other because w is a scalar multiple of u. Now, let's see the definition of a triple product of vectors and its properties. So there are two types of triple products of vectors. One is the scalar triple product and one is the vector triple product. In the scalar triple product, basically that's equal to this or this, right? Basically, you take the cross product of two of the triple product of the three vectors, right? And then you multiply, and then you take the dot product of the result with the third vector. And obviously you can take it in any sequence you want. You can first take the cross product of u and v, and then take the dot product of the resultant with w, or you can take the cross product of v and w and then multiply the result, and then take the dot product of the resultant with u, right? And so the vector triple product, instead of the dot product, it's all cross product. So basically you take the cross product of v and w, and then you take the cross product of the resultant with u. But let's just focus on the scalar triple product for now. We'll let u, v, and w be three vectors, and so the scalar triple product of the vectors u, v, and w can be written in these three forms, right? And that's what we discussed earlier. The sequence can be in any way, but the most important thing is that you take the cross product of two vectors, and then you take the dot product of the resultant with the third vector, right? So the scalar triple product can also be written down like this. Why do we write it down like this? Because it makes the calculation much simpler for us, because you can find the scalar triple product of u, v, and w by just simply solving the matrix u, v, and w, just like you did in the cross product, right? So the properties of triple scalar product: if u, v, and w are coplanar, that means they lie in the same plane, then the scalar triple product of u, v, and w will be equal to 0. And that basically means that the parallelepiped that is formed by these three vectors, the volume of the parallelepiped is equal to 0. So what this basically tells you is that the scalar triple product basically gives you the volume of the parallelepiped that is formed by the three vectors. And we'll later on discuss what the parallelepiped is, but this is just for your knowledge right now. So if any two vectors of a scalar triple product are equal, then its value is equal to 0. And that is proven basically by if you solve the matrix in which the two vectors out of the three are equal. So basically, let's say u and u, and you have v and v as the two vectors, then the result when you solve the matrix will be equal to 0, right? So the two properties are that if u, v, and w are coplanar, then the scalar triple product is equal to 0, And if any of the two vectors of the three vectors in the scalar triple product are equal, then again the scalar triple product is equal to 0. Now let's solve an example. But let's say we have ki and j, and we need to find the scalar triple product of ki and j. So ki, ai, and j is given to you as this vector here. Now remember how you solved the scalar, how you solve cross products of two vectors. We'll apply the same rule here. So basically, you'll first write down this 0 over here, right? And then you'll cancel out the column of the 0, the row of the 0, and then you'll multiply this 0 and this 0, right? And subtract from that the product of this 0 and 1, which is basically just equal to 0 again, right? Now, in case of the second 0, we'll do the same thing. So as you remember, the second one is equal to negative 0. So you cancel out its column, you cancel out its row, multiply 1 and 0, that gives you 0, and from that subtract this 0 and this 0, that gives you 0 as well. So now the third one, you take this 1 over here, right? So you write down plus 1, cancel out its column, you cancel out its row, you multiply this one and this one, so that gives you 1, and then from that you subtract 0 into 0, that gives you 0. So this basically equals, this equals to 0, this equals to 0, and this equals to 1. So the resultant of the scalar triple product of ki and j, when this is basically equal to ki and j, obviously, that gives you 1, right? And yeah, so this is equal to 1. And just another reminder why ki, I, and j is equal to this is because this first row represents the first vector, which is basically given to you as k, just k, which is why there is only 1 in the place of the k-axis, z-axis, right? And the other two are 0. The second one is I, which is why we have this one over here, and the third one is j, which is why we have this one over here. Now we have I, and k. By just using your own brain and the property that we discussed earlier, I and I, the two vectors I and I, are equal, which means that this will always give you 0. But let's prove it. I, and k. This is the vector I, because it has just this 1 over here, which represents that you only have 1 in the x-axis, or I. The second one is again the same as it is again I, so you have 1 over here. And the third one is k, which means that you'll have this one over here, right? And basically now, when you solve this using the matrix method, you take this 1 over here. So basically that means you write down this 1, cancel out its column, cancel out its row, multiply 0 and 1, that gives you 0. From that subtract 0 into 0, so 0. The second one is negative again. So what do you do? Well, cancel out its, you write down the 0, this 0 over here, and then you cancel out its row as well, and then you multiply 1 and 1, so that gives you 1, and that subtract 0 into 0, that gives you 0. And the third one is this 0 over here. So you write down the 0, you cancel out its column, you cancel out its row, 1 into 0, that gives you 0, minus 0 into 0, that gives you 0. And once you solve all of this, you find out that 1 into 0 is equal to 0, and this again 0 is multiplied with all of this, so this is also equal to 0, and this entire thing is also equal to 0. So that gives you 0. Hence you've proven. Now let's see how you can define the volume of a parallelepiped. So we've discussed earlier that the triple scalar product represents the volume of a parallelepiped having u, v, and w as its conterminous edges, right? So the vectors u, v, and w are basically the sides of the parallelepiped. And the triple scalar product will give you the volume. So let's see, this is the shape over here. So you have the base as u and v, right? In this case, this is v, this side is v. So obviously this side is also equal to v. And this side is u. And so obviously this side is also u, as they are parallel. And so now the third side that you have left is this, right? And this is w. And so this is also w. And again, you can find out by seeing that what sides are parallel. So obviously this side is also w, this side is also w, this side is v as it is parallel to v, this side is also equal to v, this side is equal to u as it is parallel to u, and this side is also parallel to u, so this is also equal to u. So you have this, let's just take this one right now. This is u, and this is v, right? And let's say this is w. Now that you have these three sides, you can see that the triple scalar product u cross v dot w is basically just equal to the magnitude of u cross v into the magnitude of w into cos theta. The angle between u cross v and w is theta, right? So in this particular case, u cross v, the magnitude u cross v basically gives you the area of the base parallelogram, right? Because this is u and this is v, and this area, the shaded region, is basically the magnitude of u cross v, right? So it is basically the base, the area of the base. And the height of the parallelepiped is equal to the magnitude of w into cos theta. Why? Because this side is w, right? And the angle between u cross v and w is equal to theta. Why is this line equal to u cross v? Because it is parallel to the plane of u and v, right? This is the plane of u and v, the shaded area. And this vector over here is perpendicular to the base u and v, right? So this is u cross v, and the angle between w and u cross v is theta, right? So w cos theta would give you this height. Let me just erase the lines that I have drawn over here, right? This height over here is basically equal to w, the magnitude of w into cos theta, and theta is this angle. So that is the height of the parallelepiped, and you just have to multiply the two to get the volume of the entire shape, which is the parallelepiped. Now, there are other ways to do this, right? You can take the base as v and w. So if you take the base as v and w, you take the cross product of v and w, and then you multiply the resultant, the cross product. You take the dot product of the resultant with u, as u will be acting as the height in this case. And let me just show you. If you take v and w, right? If you take this v and this w as the base, so this will be the base. In this case, u will be the height, right? And the third case would be if you take w and u as the base, right? In which case, well, let's just for simplicity's sake, let's take this w, right? So this is w and this is u. In which case, you'll take this as the base And then when this is the base, this v will act as the height, right? So in that case, you take the cross product of the base, the vectors that form the base, w and u, and then you take the dot product of the resultant with v. So these are the three ways in which you can basically find the volume of the parallelepiped formed by u, v, and w. Now let's find the work done by using the dot product. Now, there are two things that you must remember. To find the work done by two vectors, you use the dot product. To find the moment of force, developed by two products, you use the cross product. In this particular case, we'll need to find the work done, so we'll use the dot product. So, oops, just a second. So, in this case, it says that a particle acted by constant forces, this one and this one. So the two forces act on a particle, and the displacement of the particle is from A, which is 1, 2, 3, to B, which is 5, 4, 1. Now we need to find the work done by the particle. So we have this force F1 and this force. This is the F1 force and this is the F2 force, right? So the total force acting on the particle is the sum of F1 and F2, obviously, and that gives you this. Really simple, right? Now, the distance is A to B, right? So A to B is equal to OB minus OA. OB is the position vector of B, and OA is the position vector of A. So once you do that, you get this, right? So the work done is equal to F dot D. And once you do that, you find that this is the answer. So 36 newtons is the work done by the particle. Now let's see how we can find the moment of the force. As we've discussed earlier, you need to use the cross product in this case. We have a force F, which is equal to 3I plus 2J minus 4K, and it is applied at this point. We need to find the moment of the force about this point. Not this point, this point. So how do you do that? Well, let A be the point that the force is applied on, and let B be the point that we have to find the moment of the force about, right? So R is the vector that goes from B to A. So BA. So BA is basically equal to OA minus OB, OA being the position vector of A and B being the position vector of B, right? So that is equal to this. Now that you have this and you have F, you can simply find the moment required, and that is equal to R cross F, right? So you just find R cross F. And a reminder how to do that. You take I, you write it down, cancel out its column, cancel out its row. Now the remaining terms, these four terms, multiply the diagonals. So 0 into negative 4, that gives you 0, minus 2 into negative 1, that gives you plus 2, because minus minus is equal to plus. Then you write down J, negative J, because the second term is always negative, right? So you take this J, you write down minus J, cancel out its column, cancel out its row. Now the remaining four terms, multiply the diagonals. So negative 1 into negative 4 is equal to 4, and negative 1 into 3 is equal to negative 3, but since 4 minus negative 3, that will give you 4 plus 3, right? Now for the third term, again, the same process as you did with I. So you write down positive k. You cancel out its column, you cancel out its row. You multiply minus 1 and 2, that gives you negative 2, and subtract from that 0 into 3, which is equal to 0. And now just compute the result, and that gives you 2i minus 7j minus 2k, and this is the required moment.